In this experiment, you will learn about the Faraday effect, which is a type of a magneto-optic effect. Magneto-optic effect is the name given to the interaction between light and magnetic materials. In the Faraday effect, you have a material represented by the cylinder in which there is a magnetic field in the given direction, and the light enters the material along the direction of the magnetic field, and the light has got a polarization perpendicular to the direction of the magnetic field, and for such a beam, when it exits out of the medium, the plane of polarization is rotated by an angle beta. So this is the initial plane of polarization, and when it comes out, the plane of polarization is rotated by some angle beta. This angle beta is proportional to the length of the medium d, the strength of the magnetic field B, and the proportionality constant is known as the Faraday constant V. This is what you'll be measuring. You'll be measuring the Faraday constant for the given material in this experiment. A simple way to understand the Faraday effect is to think of a linearly polarized beam entering the medium along the direction of the applied magnetic field B, and you can decompose this linear polarization as a left circular polarization and a right circular polarization. So in one, the electric field spirals around in a clockwise manner, in the other, the electric field spirals in an anti-clockwise manner. Now inside the medium, these electric field will exert a force on the charge carriers in the medium, and but the direction they will move in will be opposite for the left and the right circular polarization. Therefore, that motion of charge will also result in a magnetic field, and therefore the induced magnetic field will also be opposite. So if for example, say the right circular polarization results in a magnetic field that adds on to the existing magnetic field, that is, the induced magnetic field is in the same direction of the existing magnetic field, then for the left circular polarization, the induced magnetic field will be in the opposite direction. So this difference can be shown to result in a phase difference in the two beams in the two components as they move through the medium, and when they recombine outside the medium, the difference in phase, or essentially the difference in speed, will result in the plane of polarization being rotated by some angle. And that's a very simple way to look at the Faraday effect. You'll need to do a full quantum mechanical treatment to understand this, which is beyond the scope of what we can do here. So to do the experiment, first let's say there is some kind of beam that enters in this direction, and there is a polarizer. So a polarizer is some substance which will filter light polarization. So if the optical axis of the polarizer is in this direction, then only light polarized in parallel to the optic axis will be filtered out of the polarizer. So you now have light which is polarized like this. Now if you take a second polarizer, which is called an analyzer, and if you place it such that its optic axis is perpendicular to the optic axis of the first polarizer, that's called a crossed polarizer arrangement, then the light intensity will be minimum. So basically it will filter out this polarized light as well, and the light intensity will be minimum. Now if you have this arrangement set up, and if you introduce the medium in the middle and apply a magnetic field, so you have this arrangement, you put the medium inside and apply a magnetic field, then basically there will be the light intensity will no longer be minimum, because the plane of polarization is now rotated, and therefore some light will pass through the second polarizer or the analyzer as well. So to find out the new minimum, you have to rotate the polarizer by some angle, and that angle is basically the angle beta, which is the shift in the plane of polarization. So this is how you do the experiment. So you basically have the material which is placed inside a solenoid. So you have to pass different currents through the solenoid to create different magnetic fields, and for every magnetic field you have to find out the angle of rotation. So you basically start from this arrangement where you have the polarizers are initially crossed and the light intensity is minimum. Then when you introduce the medium and if you start increasing the current, which will result in a different different values of magnetic field. For every value of magnetic field, you will have to find out how much you need to rotate the polarizer to create a minimum again. So that gives you the angle beta. So there is a video associated with this experiment which you have to watch, and watch it once to understand what's happening, and then you can see the person taking the readings. Please pause it and note down the readings. So you will have let's say these are the currents applied to the solenoid. Note down the analyzer angle, and from that find out the beta, that is the change in the angle, and create, and then from that you can calculate the magnetic field. The parameters of the solenoid are given here, or you can find it in the manual. The wavelength of the laser is 532 nanometers. So then you can just plot the beta as a function of the current and calculate the slope and find out the Faraday constant. So it's a fairly simple experiment. Please read the manual once and then use these parameters. Watch the video, the next video once, understand what's happening, and then take measurements from that, record measurements by pausing the video from time to time, and then calculate the Faraday constant.